So today I'm going to talk about the vectorized execution in Apache Spark, which is new in Spark 3.0. And my name is Hyukjin Kwon. I'm a software engineer at Databricks, and then I'm not an expert in R or like in CPU or vectorization, but I mean I have learned and then I have implemented in the Apache Spark. So I want to share what I've learned and then what I've implemented. So me, Hyukjin Kwon, and then I'm a Apache Spark PMC and committer, and also I'm one of the Koalas committer, and then I'm the top contributor in Koalas. My interest in is actually PySpark and SQL, and then SparkR, and then I do a bit of infra stuff and build. I'm pretty active in GitHub, Apache Spark, so if you guys see me and then just say hello. So this is the agenda. Today I'm going through the SparkR and R interactions because basically the SparkR, it needs to launch a R process and then it interacts with the JVM. And then I'm going to talk about the current implementation in SparkR and then Apache Arrow and then how I integrated the Apache Arrow and then implemented vectorized implementation. And there are a couple of future works to be done, so I'm gonna go through this. So SparkR and R interaction. When you execute some R APIs, then you see time to time, like the performance is basically the same. Like in particular, you use like some SQL APIs, like count, like something. Then I did like a bit of like simple example here, and then it gives like basic almost same performance, which is pretty good. In most cases, it gives similar performance, but in some cases you see like some weird performance penalty a lot. In this case, it's like 12 times lower. Like, but virtually they are same codes. So basically, it calculates the summation of each partition, and then I just calculate the count, and then in our side, it does the exactly same thing, but performance is suddenly like become 12 times lower. And this case is actually a bit worse. Like it became like 40 times lower. Like it's basically like same APIs. So I just used like select from like range, and then I just call collect, and then it suddenly like become like 40 times lower. It's a bit weird, right? The problem is basically that there is like conversion from R primitive type to JVM primitive type, or sometimes it requires to execute the R native function, and then for such cases it brings some overhead. So I'm gonna show you the 4 APIs that bring such performance penalty. One of those is createDataFrame. So SparkR has a DataFrame, the createDataFrame APIs. So basically, it creates a Spark DataFrame from R DataFrame or list of lists of the R primitive types. So this is like simple example. So in this case, it requires to convert the R primitive type to JVM type. I'm gonna tell you about in more details later. One of the slow API is collect. So you collect, and then this collect is basically create R DataFrame from Spark DataFrame. So it basically collect everything at the worker node to the driver, and then converts the JVM the data to R DataFrame. So those two APIs are related. They are primitive data types. And then in case of when it requires to execute R native function, one of the APIs is dapply. So with this API, you can apply the R native function as is. So in case of like this simple example, it applies a function to each partition, and then in the function, the argument, it becomes R DataFrame. So you can apply a function with R API for each partition with this API. And lastly, gapply. It's actually this kind of API doesn't exist in SQL, but it only exists like in SparkR and PySpark with Pandas UDF. Basically, the approach is group and map. So it groups by a given key, and then you can apply the function, but the group here in this function becomes R DataFrame. So you can apply a function to each group with R APIs. So those APIs are slow, and then in current implementation, I'm not sure why it's slow. Here's a brief overview of SparkR. So it's R API basically, right? So it needs R process to execute some R APIs. So basically the R process, like here. Oh, cannot. Oops. Okay. So basically at driver side, the left side, the R process, right? It connects with the JVM. So it like just sends some data, like for instance, like class name and the method name, and then it calls some like Java function, and then it's called in JVM. This protocol is defined, and then it uses a socket. And then when it connect and then like use some you can use when you use like SQL APIs, then most of operations happens within the JVM. It actually doesn't launch our process in most cases. In this case, it gives like almost same performance. But in particular cases like dapply or gapply, when you execute the R native function, then it requires to launch the R process. Like right side, you see these two are workers, and then these two workers needs to run R process, and then it executes the R native function, and then it returns. So except that, like reading or writing from different data source or like S3 or like Parquet or C, that all things happens within JVM. So for this case, there's no performance penalty. But when there's interaction between R and JVM, there's always performance penalty. So I'm gonna tell you a bit more detail about the driver implementation, because driver implementation matters for the createDataFrame and then collect. In case of SparkR, it actually SparkR shell, the flow is a bit different. So this slide, I'm gonna just tell you about first the application submission. So you like Spark submit like script.r, and then if you submit the R application, first at JVM it launches something called R backend. Within JVM, it's JVM instance, and then this creates a server, and then wait for connections, and then this JVM launches a R process. This R process establishes a connection to the server created before, and then it started to execute the R script you submitted. Within the R script, you use SparkR API, right? And then this SparkR API calls JVM functions. For instance, like as I said, like class name and then function, and then just like that. And then the R process send the like class name and then argument function name to the JVM, and then the function is executed. It's fine in most cases because it's like name, but sometimes the R side needs to like send some actual data like row by row, and then I made the row by row red because it matters. I'm gonna tell you a bit of details later. So this is like rough graph. createDataFrame and the collect matters, right? So here is driver side, and then when the in case of createDataFrame, which converts R DataFrame to Spark DataFrame, under the hood it actually make a RDD, just binary RDD, and this RDD contains the R data as is, just binary raw R data, just R types. And then later on in JVM, each R data is manually one-to-one matched to the JVM type. So for instance, like R int becomes like JVM integer or int, things like that. After that, since we know each JVM types, then we can create the data frame, right? This is what happens when you create the data frame in SparkR. Then when you call collect, it's just basically in opposite manner. The data frame becomes a binary RDD, and then this binary contains the R data type, and then this is of course matched one-to-one within JVM type, and it's collected to the R side, and then it becomes list of list, and then you create it. It creates the data frame from the list of list. That's it. Here the problem is it sends row by row, and then serialize, deserialize in a really inefficient manner because the data is just being sent in raw manner without any like compression or encoding or something. And then this is worker implementation. This worker implementation matters for dapply and gapply, like R native function execution. So when you execute something like some job or things like that, and then here's the worker side. And the worker side, when it's required, it launches some R process. Within JVM, there's a something called its class, something called R runner. So this R runner launches a R process, and then through this socket, it sends some data to the R process. And then this R process receives the data and then the serialized function to execute. And then when it receives the data, it also receives the data row by row. After executing the function, it sends the result back to the data JVM type. And of course, in this case, the function takes R data frames. Each row has to be converted back to the JVM side, like one-to-one. Yeah, like match, like if like it's R integer, then return JVM integer, things like that. As I said, the dapply and gapply matters. This is a diagram at worker side. So the purple one is JVM, the blue one is R side. When there's no like SQL, there's no like dapply or gapply, such things doesn't happen. The physical operator just like it doesn't have R runner and it doesn't launch. But like when you use dapply or gapply, whenever you use, it launches something called R runner, and then it launches the R process, send the data, and then execute the function, and then you send the data row by row. Okay, so it's pretty slow. I'm gonna tell you why here. So I had to use Apache Arrow, and then I integrated this, and then I implemented the vectorized implementation. Apache Arrow is basically a cross-language development platform for in-memory data. It's basically a columnar data format. So you can think it's like just data format, but like for in-memory store. Currently, in the Apache Spark master, it supports SparkR from 0.12, but since at actual Spark 3.0, I think it will be 0.15. So it's not decided yet. Why the Arrow is important? The Apache Arrow enables vectorization itself, so you can just use it. Since the Arrow has the columnar format, it enables us to do like vectorized like batch operation. So here's the SIMD, which means single instruction and multiple data. So usually, like you have to like one instruction and then two operand, right? And at the CPU level. So the PC increase and the one by one, and then it executes the instruction one by one. But in some cases, there might be one instruction, and then for instance, like array A or array B, right? You can do it like vectorized operation. In actual CPU level, there's something called pipelining. So let's say you read integer, right? You read integer, and then let's say this, here's ABCD, right? let's say read integer from A, and then the ABCD might be like fetch A and then like, move to somewhere, and then C might be like, something else. So this ABCD is like one block, like reading int. And then if you like do these same operations again and again, the CPU can predict, and then it can just it can execute this kind of instruction like in a pipelining, as you can see. So like at the right side, right? Yeah, right side, it's like there are 4 CPUs, and then there are like 10 clocks, and then the ABCD, like let's say reading int, is the all same like operations, right? So you can do it in pipelining. Like you don't have to wait for the whole block to be finished. But let's say like you read like different thing, like reading int, and then after that you want to do something, and then it's like reading string. It's different operation, and then the pipeline is broken. So the actual computation takes longer. So here what I'm trying to say is vectorization is in columnar format. It allows you to do the same operation, right? For instance, in integer column, you read it and then you read int. If it's like row-based format, then you, for instance, like row has like integer and string, and then you read int and then read string, so it requires to the like different instruction, which blocks pipelines. And also Apache Arrow basically targets no copy, and then seems like 70 or 80% of computation is like wasted like serialization or deserialization. Each project has its own format to be stored, so such a thing brings some overhead. So Arrow came out to have like deduplicated across the project, have like one format, and then it can be shared with no copy. So basically Arrow targets this. One of the things we should take into account is serialization and deserialization. When Apache Spark use some like send the data, right? I told you, right? It's like when it just send the raw data, like without any encoding or compression or things like that. But Arrow format itself support like dictionary encoding or like run length encoding or something like that. So you can actually use the less I/O, which can be more performant. So each Arrow batch itself is portable data frame. Then each Arrow batch can be Pandas DataFrame or like R DataFrame or like JVM instance. This can be sent to like from A to B, and then it directly can be used in B site. So it can share data algorithm, and it targets zero cost. All right, so now we know Arrow. So I'm gonna show you how I use this vectorization. I'm gonna talk about the createDataFrame and collect first. In Apache Spark, there's a class like Arrow reader and Arrow writer, and most of Arrow implementation within Spark use these two classes. There are some codes if you guys are interested in. So you guys can, like the code pointers below, communicate JVM and R workers via socket. So this is a previous original implementation, right? It creates a RDD binary, and then it becomes data frame, and then when you collect, it becomes binary again, and then the binary becomes our data frame, right? Now with this Arrow optimization, it can be all done with Arrow batch. So when it creates data frame, it converts the R DataFrame into Arrow batch, and then it's sent to the JVM. Then the Arrow batch becomes Spark DataFrame. So it's fast due to two reasons I just described just now. Like one reason, vectorization, because it can do the batch read and write. And then second reason is that it actually used less I/O, because previously it used like raw like encoding, like raw data as is, but now it sends like lots of encoding and it sends less data. So I did some benchmark, and then it becomes, in case of createDataFrame, it became 17 times faster, and then in case of collect, it became 42 times faster. And then I also tested with the existing SparkR test within Apache Spark, and then all tests passed. So I think it's able to use. And then I've observed that then the more the number of rows grows, then the more performance gain you get. Then this is, so now it's about dapply and gapply. Here is about the R native function execution, and then it also uses the same arrow writer and arrow reader within Apache Spark. I've also wrote the code pointers. I said it used R runner like before, right? Now it uses something called different R runner, arrow R runner. And then when the SQL usually have some like physical plans, right? For computation, and then for this vectorized execution, it has its own physical plans. It's like map partition in R with arrow, and then flat map groups in R with arrow. So here's the existing implementation, and then it's similar. Like it instead of like sending by row, it groups, and then the group of rows becomes arrow batch. Then likewise, it saves like serialization, deserialization cost. Then you can do vectorized operations. Also, I did some benchmark. So in case of this, 43% faster, and then gapply become 33 times faster. So likewise, all related tests passed. So you can just switch on the configuration, and then you can experience the this improvement. Just in case of you guys don't believe, and then just in case you guys want to try it out, I wrote some notebook, and then I found some like kind of web service. So it's like, I'm gonna show you. It launches a live Jupyter notebook, so you can just use it right away. So here's something called Binder. It takes a couple of minutes. So I did it. Oops. No. Okay, let's wait. It takes a couple of minutes, because basically what it is, like, it clones from GitHub, and then it launches a Docker container, and then it starts the Jupyter server, so you can use it. Here's basically the benchmark I did. It downloads some data, but the data is like a bit small. In particular, in case of this notebook, seems like the Docker container doesn't have like lots of resources, so I just did like small data source up to like 10 megabyte. Okay, you go. So when you use like larger data, which is linked here, you can actually do it. You can try it by your local It has more improvement. So I do enable something called R shell magic to use R. Here it downloads the data. It's like regular CSV data. And then I extract, launch the SparkR. I'm gonna use something called micro benchmark to show the nice graph. And then prepare the data. And then you can just run some benchmark like this. So if you doubt or you want to try out, then go to this link, and then you can actually try by yourself. All right. So okay, take a picture. All right. So here is the last item. There are some future works to be done. I actually lied. There are some problem here. Like it doesn't send the arrow batch like batch by batch in a streaming manner because there is an issue in Apache Arrow. So you cannot use the socket itself like when you send or receive the data. So like I had to buffer everything. For instance, like one partition buffer everything and then send it once. So it has to be fixed. So it's not really streaming, but it's like you send the whole arrow batch once. So it has to be fixed. So if you guys know some guy in Apache Arrow, then please fix it. And then there's actually another API called dapply_collect. You can omit the schema. It's basically shortcut for dapply and collect. But currently this isn't implemented. gapply too. gapply collect, and then you can omit the schema, but like it's not implemented. Actually, it looks simple, right? It's just like it looks like shortcut, and then you can just omit the schema, and that's it. But why it's not implemented? There's actually a problem. Spark itself is like based on lazy execution, right? So you should know the return type, the what will be returned. Then you should know it. Like that's why you should you should give the schema to the dapply. But if you omit the return schema, then you don't know what's going to be returned. So like you should execute the given R function. Otherwise, you don't know what's the return schema type. So the approach to solve this case is like bypass the schema. So you don't use the schema, but just use binary type. And then you just collect as is at the R side, and then convert this binary itself to the arrow batch, and then R DataFrame. So in this way, you can bypass, but it needs a bit of code, so it might not be available in Apache Spark 3. All right, so I have so many people actually helped me. Actually, I did it like by myself based on my own interest. So many people from Flex, Chang from Uber, he's a SparkR committer in PMC, he helped me. Brian Kotler, Arrow committer and Spark committer, and then Yang Chi, Hirosin Takuya, Yambo, they all helped me a lot. So I'd like to thank them. That's it. So thank you so much.
Thank you very much. We have a couple minutes for questions, and so if anybody has a question, I can run a microphone.
Hi, thanks for the talk. I actually have a question for the vectorization part. So, can you talk a little bit more about how the Spark in memory format convert to the array format, and then why the so I understand the part that if we use unsafe row and we convert it to array and to do the serialized deserialization, it must be faster than the default serialization deserialization. But how you convert the unsafe row to the vector of arrow and do the serialized deserialization part? Are you buffering of the unsafe row?
Sorry, can you make this
So I think because in the hosted code gen of Spark, so we use unsafe row.
Yeah.
And how you is you buffering the array of unsafe row and to change it to the array vector of arrow and send it to the R process?
Actually, the Apache Spark itself doesn't use for like tungsten or its own doesn't use Apache Arrow for like tungsten or unsafe like data itself. It has its own implementation. Then it doesn't use Arrow, so it's a bit separate question. But basically, so you're talking about like how Apache Spark unsafe or like internally use vectorization, or yeah. Let's talk. Yeah. Sorry. Yeah.
There's another question. Anybody else have another question? Going once, going twice. Cool. Thank you very much.
All right. Thank you so much.